Okay, so now we are going to start with the refrigeration. Okay, so it is a complete new chapter, and the concept of it was given in the open system works. Okay, so this is the, or you can say in the second law. Okay, in the second law the concept of refrigeration was given in a brief way, but we did not analyze any of the cycles which is related to the refrigeration. Okay, so now we are going to start with the refrigeration. Okay, now what is refrigeration? Refrigeration is nothing but it is the process of creating a temperature which is lower than the surrounding temperature. Okay, that means to create a temperature lower than the surrounding temperature and to maintain that temperature, okay, is going to be known as refrigeration, or the process of refrigeration. Okay, so if you imagine the refrigeration that has been present in your room, okay, so the space that has been covered by the refrigeration, okay, or if you open the door, you can feel the temperature inside this is going to be very lower. That means what? The temperature inside that space in a refrigeration, okay, whatever the space that has been confined by its insulated covers, that space inside the that space, okay, which has been inside this refrigeration is maintaining a temperature which is lower than the atmospheric temperature. Okay, so refrigeration or a refrigerator, okay, is having two purposes. Okay, one is to create the temperature lower than the atmospheric temperature, okay, and the another purpose is to maintain the temperature. Okay, it's not like once you have created the temperature and it will be continuously there without any effort. It is not like that. If it would have been the case, then you could have made ice out of water and you could have kept it outside, then it would have been ice for all day long. Okay, but this is not the case here. Creating the ice out of the water is half of the work done by the refrigeration. Okay, we are creating the temperature lower than the atmospheric temperature, but to keep the ice intact, okay, to keep the ice intact, what do we need? We need to maintain the temperature lower than or at least equal to 0 degrees centigrade. Okay, so how can it be done? It can only be possible if the process which has made this temperature lower than the atmospheric temperature, that must be in continuous cycle. Okay, so if there is continuous cycle going on, then only it is possible to maintain the temperature lower than the atmospheric temperature. Okay, so if you want to know the refrigeration, it is a process of creating and maintaining the lower temperature than surrounding, and it must operate on a cycle. Okay, so the two purposes are creating temperature, okay, creating the temperature lower than the atmospheric temperature, and to operate on a cycle so that we can maintain that lower temperature. Okay, so this is going to be the complete scenario of refrigeration. Now one thing we might remember, that the refrigeration is always going to be work consuming cycle. Okay, it is going to be work consuming cycle, and in the first law we have said that when a cycle is clockwise, it is representing a work producing cycle. Okay, when a cycle is clockwise, it is work producing cycle. But when the cycle is anti-clockwise, okay, when the cycle is anti-clockwise, that means what? That cycle is power consuming cycle. We are giving power to make it do something. Okay, so in refrigeration, what is done? Okay, it is a refrigeration. So in refrigeration, what is done? We give some work. Okay, we give some work, and some of the heat is taken out from a space. Okay, so that the space is maintaining a temperature of TL, okay, or lower temperature, and the remaining heat has been transferred to the surrounding, okay, or any other thermal reservoir you can take. Practically we take here the thermal reservoir is atmosphere. Okay, so we reject the heat to the atmosphere. Okay, now why do we need to give work as input in case of refrigeration? Because in case of refrigeration, we are pulling out the heat from lower temperature and giving it to a higher temperature, but that is not a spontaneous case. Okay, the spontaneous things are what? Which is done by nature. Okay, the natural things are known as the spontaneous things. Spontaneous thing means what? Without any effort, it is going to be happening. Okay, so if you think water is coming out of the hill, okay, or water is coming down through hill, this is a spontaneous process. But water going up to a hill, that is not a spontaneous process. That we need to do some work for taking the water to above the hill. Okay, to climb up the hill, we need to do some work so that the water can go up to a certain level of height. But in natural, okay, in natural or in spontaneous cases, what happens, the water is automatically coming down. Okay, so that means what, the nature is having a law for the spontaneous work to be done. That means all the processes that is going to take place always takes place from higher potential to lower potential. Okay, so in case of water, the example of water, that is water is coming out of the hill, it is always going from upper height, okay, or you can say higher head to lower head. Okay, water always flows from higher head to lower head. Okay, now to reverse this process, means what, we need to take the water to a greater height, okay, or to a greater altitude. Okay, so what do we do then? Remember, or you can imagine the overhead tank in your house. Okay, overhead tank in your house where you can pull the or give the water. Okay, where you can give the water so that you can use it for future purpose. Okay, so what is the procedure for the water to reach in the overhead tank? That is nothing but you must use a pump. Okay, now pump is what? Pump is work consuming device, and we are going against the nature. Okay, we are going against the nature. Against the nature means what? Generally water comes down, we are now trying to pull up the water to a certain height, so obviously some work has to be done. Okay, some work has to be done, and that work is done by the pump. Okay, that work is done by the pump. So to pull the water from lower gradient to high to pull the water from lower altitude to higher altitude, we are giving some work with the help of the pump. Without the pump, or without work being given to a system, you cannot reverse the spontaneous system. Similarly, in refrigeration, heat always flows from higher temperature to lower temperature, which is the case of heat engine. Okay, in heat engine what happens, we give heat and it goes to lower temperature from higher temperature. Okay, now we are trying to do what? The surrounding temperature is higher. Okay, surrounding temperature is higher, and that space where we are trying to maintain a temperature lower than the atmospheric temperature is going to have a lower temperature. So in general case, if you put these two reservoirs side by side, what will happen? Heat from higher temperature will go to lower temperature. Okay, that means the space we are maintaining will gain some heat due to the spontaneous action of the nature. Now what we are doing, we need to reverse this. We need to take the heat out from the lower temperature and give it to a higher temperature. Similarly, like taking water from lower altitude and giving it to the higher altitude. Similarly here, taking the work from taking the heat from lower temperature and giving it to higher temperature is against the nature. So to go against the nature, we need to give some work. That is the reason why in refrigeration we give some work so that the heat goes up from a lower temperature to a higher temperature. Okay, and to maintain this temperature, this is the system which is continuously running on cycle. Okay, without cycle you cannot maintain this temperature. So this is, and this has been represented as anti-clockwise cycle. Why it has been represented by anti-clockwise? Because anti-clockwise cycle always represents that it is power consuming. As refrigeration is power consuming, that's why the cycle that would be there would be anti-clockwise. Okay, anti-clockwise. So this is the refrigeration concept. Okay, now coming to refrigerant. What is refrigerant? Refrigerant is nothing but it is a substance with the help of which the creation of the temperature less than atmospheric temperature is going to take place. Okay, it is the substance. Okay, now in some of the cases it is a substance which is taken in such a way that it evaporates at temperature less than atmospheric temperature only. Okay, so that means what? Suppose there is a turbine, and there is a compressor. Okay, there is a turbine and there is a compressor, and there is going to be a heat rejection system, and there is going to be a evaporator. Evaporator means what? In evaporator, all the liquid is going to now evaporate. All the liquid is now going to get evaporated and perfect steam will come out. Okay, steam will come out. So this device is known as evaporator. Okay, so what does this refrigerant do? Okay, so we take the refrigerant in such a way. We are taking a particular case. Okay, in particular case, that means we are just maintaining a temperature lower than the atmospheric temperature. We are not going to a particular temperature that we are needed to maintain a temperature of minus 180 degrees centigrade. No, we are taking a particular condition that is keeping the temperature lower than atmospheric temperature. That is our motive, nothing else. Okay, for this particular case we are going to explain this example. Okay, so what is going to be there? Suppose the substance is coming out in evaporator. Okay, after expanding, this is a turbine. Okay, sorry, we have drawn it in different way. This is going to be a compressor and this is going to be a turbine. Okay, so that means what? This is a turbine. So after expanding from the turbine, always the liquid comes out. Okay, so liquid is now passing through the evaporator, and the substance is chosen in such a way that the substance is having a boiling point temperature less than the atmospheric temperature. Okay, that means what? Suppose your surrounding temperature is 25 degrees centigrade. Now we will choose one of the refrigerant in such a way that its boiling point temperature is going to be, suppose, 10 degrees centigrade. In 10 degrees centigrade, automatically it evaporates or it boils. Boils means what? The complete liquid is now converted to vapor. Okay, so the substance which we are going to use will automatically evaporate in 10 degrees centigrade only. Okay, now due to this evaporation, what will happen? During any phase change process, there is some latent heat involved. Okay, there is some latent heat involved. Okay, so during this evaporation process, it takes out the latent heat of evaporation. Okay, during phase change there is always some latent heat. Okay, so during while it is evaporating in the evaporator, okay, it is taking some latent heat of evaporation from the space, okay, where the evaporator is kept. Okay, where the evaporator is kept, from there it takes the latent heat of evaporation, and due to this, heat is continuously being going up. Okay, or heat is continuously being rejected by the space. Okay, where we are maintaining the temperature. So after this evaporator, after the vapor that is coming out from the evaporator, it is passed through a compressor. After that, the heat is rejected, and after that it is again expanded through a turbine, and in this way the cycle works. So basically, refrigerant is what? Refrigerant is a substance which helps us to maintain the temperature or to create the temperature lower than the atmospheric temperature, or a temperature which is required. Okay, or a temperature which is required. So for this reason, refrigerant is used. Now, refrigeration effect. What is going to be refrigeration effect? Refrigeration effect is the amount of heat that is taken out from the space so that we can create the temperature we need. Okay, suppose we need to create a temperature of 5 degrees centigrade. Okay, so, and it is presently in a temperature with the temperature equilibrium with the surrounding of, suppose, 27 degrees centigrade. Now from 27 degrees centigrade we need to take it to 5 degrees centigrade. Now to take the temperature of that space from 27 degrees centigrade to 5 degrees centigrade, the amount of heat that has been taken out from that space is known as the refrigeration effect. Okay, this is the refrigeration effect. So now we are going to study the units of refrigeration. Okay, so the first thing is ton of refrigeration. Ton of refrigeration is an unit of refrigeration. Okay, now what does 1 ton of refrigeration means? Okay, so 1 ton of refrigeration means the amount of heat that has to be taken out from 1 ton of water, that means 1000 kg of water at 0 degrees centigrade, to convert that whole amount of water, okay, the whole mass of water into ice at 0 degrees centigrade in total of 24 hours. Then that amount of heat that has been taken out to convert the water to ice, then that amount of heat is known as 1 ton of refrigeration. Okay, so suppose this is the container, and in this there is 1 ton of refrigeration, that is 1000 kg of water is present here at 0 degrees centigrade. Okay, so we need to take out the heat from this water so that the water at 0 degree becomes ice at 0 degree centigrade. Okay, so in 24 hours, the amount of heat that has to be taken out from this part so that the complete water is now converted to ice at 0 degree centigrade, then the amount of heat is known as 1 ton of refrigeration. Okay, so this is 1000 kg of water. So this is known as 1 ton of refrigeration, and 1 ton of refrigeration is equivalent to 3.5 kilowatt. Okay, so 1 ton of refrigeration is equivalent to 3.5 kilowatt. So in any place, if it is given that 1 ton of refrigeration, for converting 1 ton of refrigeration or for taking out 1 ton of refrigeration, then you can blindly use 3.5 kilowatt in that place of 1 ton of refrigeration. Okay. Okay, so now before starting the refrigeration cycles, okay, we all know that before starting a cycle we need one idealized cycle, okay, or one ideal cycle through which we can compare the other real cycles. Okay, so ideal cycle which is present there is going to be for our theoretical reference. Okay, so for comparison with this idealized cycle, we have different real cycles. Real cycle means the cycles which act in, or the cycle on basis of which the refrigeration or any other, or the, you can say, steam power plant or refrigeration or air standard power cycle, everything is going to act on the basis of certain cycles. Okay, certain cycles like Breton cycle, Otto cycle, diesel cycle, Rankine cycle, it is going to act on certain cycles. Okay, but for every cycle, for the reference of the efficiencies, we need one ideal cycle. Okay, and that ideal cycle for each and every process or each and every plant is going to be the Carnot cycle only. Okay, so in the steam power plant we have also found out the Carnot cycle. In the refrigeration also, the ideal cycle, the main ideal refrigeration cycle is nothing but the reverse Carnot cycle. Okay, it is going to be reverse Carnot cycle. Now why it is reversed? The Carnot cycle is generally in clockwise direction. If we reverse that same Carnot cycle, we are going to get the refrigeration. Okay, we are going to get the phenomenon of refrigeration if we reverse this cycle. Reverse this cycle means what? Previously it was in clockwise direction, now it is going to be anti-clockwise direction. Okay, so in the last board, as I have told, okay, so whatever the product that has been coming out from the evaporator is now compressed. Okay, by compressing it, the entropy of it is going to get increased, and temperature is also going to increase. Okay, so after that it is passed through a condenser. Okay, condenser means what? Condenser, you can say it is one of the heat rejection process. Okay, so in the condenser the heat rejection process takes place. So after that, whatever the products that is remaining, it is expanded through the turbine. So after expansion, the complete cooled thing, now it is going, now after expanding, it is going to lose its enthalpy also. Enthalpy means it is going to lose its heat content also. So after losing the heat content, the thing that is coming out would be cooled down now. Okay, now that cold thing will again pass through the evaporator, and in evaporator what happens? There is continuously phase change, and due to this evaporation, this amount of heat Q2, okay, or you can say the refrigeration effect. Refrigeration effect means what? The amount of heat that is taken out from the space so that we can maintain a temperature lower than the atmospheric temperature. So due to this evaporation, this Q2 amount of heat is going out as latent heat. Okay, as latent heat, it is going to be going out from the space where we need to maintain the temperature. So this is the PV diagram, and this is the temperature entropy diagram for reverse Carnot cycle. Okay, so previously Carnot cycle used to start from here. Okay, adiabatic compression and then expansion, then again adiabatic expansion, sorry, adiabatic heat addition, then adiabatic expansion, then again adiabatic heat rejection. Now in this refrigeration cycle, this is going to be completely reversed. Now it will start from here. 1 to 2 is going to be adiabatic compression. Okay, 2 to 3 is going to be adiabatic isothermal heat rejection. Okay, in Carnot cycle, the heat input process was isothermal. Now the heat rejection process would be isothermal. Again 3 to 4 would be expansion. Okay, 3 to 4 would be expansion in the turbine. After that, it is going to take out heat from the, or you can say heat input to the system now. Okay, heat input to the system is now from 4 to 1. Okay, similarly in temperature entropy diagram, this is 1 to 2 is reversible adiabatic, that means isentropic, so it is parallel to the T axis. 2 to 3 is isothermal process, so it is again parallel to the entropy axis. 3 to 4 is again isentropic process, okay, or adiabatic expansion process, so it is going to be parallel to the T axis. And the final thing is 4 to 1, that is heat addition to the system. Okay, or you can say the heat that has been added to the system, okay, or taken out from the space where you need to maintain a temperature. So 4 to 1 is nothing but heat input to the system. Okay, so this is going to be our ideal cycle, that is reverse Carnot cycle. Now if you want to find out the COP is what? COP is the amount of heat. Okay, the concept of COP has also been discussed in the second law. Okay, so what is COP? COP is nothing but what is the amount of heat that is, or the required effect. Okay, the required effect. So what is the effect we require now? the thing we need to know is that what is the amount of heat that is taken out from the space. So this is going to be nothing but refrigeration effect, or you can write Q2. Okay, or you can write Q2. And what is going to be the input? The input is nothing but whatever the work input you are going to give with the help of this compressor is going to be in the denominator. So this ratio is going to give you the COP. Okay, now we have again seen that, okay, the COP, and write again that what is going to be COP? COP is nothing but refrigeration effect divided by the work input. Okay, divided by this work input. Now here you can write the mass flow rate by mass flow rate. Mass flow rate is what? Mass flow rate is the mass flow rate of substance, okay, or the refrigerant. Mass flow rate of refrigerant which is continuously moving in a cycle, okay, to make the process of refrigeration work. Okay, so the mass flow rate of that substance is going to be m dot. Okay, so we can write m dot by m dot. Okay, so Re is what? Re is the refrigeration effect. Okay, so if you multiply Re with the mass flow rate, it is going to give you the refrigeration capacity. Okay, mass flow rate, if you multiply refrigeration effect with mass flow rate, it is going to give you the refrigeration capacity. Okay, now this is going to be COP. So Re into m, this thing, okay, Re into m dot, this thing gives you what? This thing gives you the refrigeration capacity. So it will give you refrigeration capacity. And we have told earlier also that work input, okay, work input into mass flow rate, or work into mass flow rate is what? It is nothing but power input. Okay, so you can also find out it like this. COP is what? COP is RC divided by power input, that is going to give you the coefficient of performance. Okay, now let us see a question. Okay, the question goes like this: a Carnot refrigeration requires 1.5 kilowatt per ton of refrigeration to find the and then find the COP. Okay, that means they have a Carnot engine. Okay, they have a Carnot reverse Carnot engine. That is a Carnot refrigerator which requires 1.5 kilowatt power. Okay, so in Carnot, in any refrigeration, the energy is given to a system in terms of work. Okay, in terms of work. So Carnot engine requires 1.5 kilowatt per ton of refrigeration, means this is the amount of work we need to give it. Okay, so per ton of refrigeration means to take out 1 ton of refrigeration from the space where we need to maintain a temperature lower than the said temperature. Okay, so this is the amount of heat we need to require to which we need to take out, and this is going to be the amount of work that we need to give into a Carnot engine, so that we can find out the COP. Okay, now this is a Carnot refrigeration, but in Carnot refrigeration there are different parts: compressor, turbine, condenser, evaporator, everything is given. But from this question we are not getting particularly to any of the parts, machine parts. Okay, so we need not consider the PV diagram or TS diagram or the complete diagram for Carnot cycle. We can easily do it from this simple layout only. Okay, this is going to be refrigeration, and this is going to be higher temperature, and this is going to be lower temperature, from where we need to take out 1 ton of refrigeration. Okay, because they have given per ton 1.5 kilowatt is required. Okay, now this is going to be the layout. Okay, so this heat is going to be QH. Okay, the amount of heat that has been transferred to the reservoir with higher temperature. Okay, and this is going to be QL. Okay, so QH we need to find out. QL is what? QL is nothing but the amount of heat we need to take out from the lower temperature reservoir, that is given as 1 TR. Okay, 1 TR. 1 TR means 1 ton of refrigeration, which is again 3.5 kilowatt, which we have said in the last board, and it requires a work of how much? It requires a work of 1.5 kilowatt. Okay, now to find out the COP. Okay, to find out the COP. COP is what? COP is nothing but the required effect divided by, what is going to be the required effect? Required effect divided by the amount of energy we are giving in as input. Okay, so that is what? That is work input, you can say. Okay, so what is the required effect here? That means the amount of heat that has to be taken out is 3.5. Okay, this is going to be 3.5, and we need to find what is going to be the work input. Work input is nothing but 1.5 kilowatt. So 3.5 by 1.5, this is going to be 2.33. Okay, so this is a very basic thing for finding out the COP. Okay, so this is going to be the layout from which we need to find out what are the different energy inputs and outputs through the first law of thermodynamics for a cycle, and after that, if you get the required values, then you can easily find out the COP of the refrigeration. Okay. Now let us see another question. Okay, the question reads like this: refrigeration works in a temperature limits of minus 30 degrees centigrade and 32 degrees centigrade. Okay, the actual COP of the refrigeration is 0.7 times of the maximum COP. Okay, so find the power input for a RC. RC means refrigeration capacity of 5 kilowatt. Okay, so they have given us the temperature limits. Okay, this is going to be the lower temperature limit, and this is going to be the higher temperature limit. Okay, and a refrigeration capacity of 5 kilowatt is given, and it is also mentioned that the actual capacity of the refrigeration is going to be 0.7 times the maximum COP. Okay, so this is the complete question. Okay, that means there are two temperature limits. Okay, two temperature limits. There is a refrigeration capacity of 5 kilowatt. Okay, so this is refrigeration capacity of 5 kilowatt. For that, what is going to be the power input? Okay, what is going to be the power input that you require to need, require to find out? But they have also given the condition that whatever the system it is working on, it is obviously going to be 0.75% of the maximum COP. Okay, now this refrigeration is running on a cycle, but what cycle they did not mention. Okay, the cycle they did not mention. It could be Carnot cycle, reverse Carnot cycle, it could be reverse Breton cycle, it could be any cycle. Okay, but we also know that the maximum efficiency and the maximum coefficient of performance is only given by only one ideal cycle, that is Carnot cycle. Okay, whether it may be efficiency, Carnot cycle gives the maximum efficiency. Similarly, reverse Carnot cycle is going to give you the maximum coefficient of performance, or maximum COP is only given by the reversed Carnot cycle. Okay, so if you consider a reverse Carnot cycle, okay, we all know that COP is what? COP of refrigeration is what? COP of refrigeration we have already found out in the concept of refrigeration, that COP of refrigeration is nothing but QL divided by QH minus QL. Okay, this is the formula of refrigeration. But while finding the Carnot refrigeration, we have replaced this Q term with temperature term. Okay, so this is going to give us the maximum COP. Okay, this is going to give us the maximum COP. Why? Because we know that if efficiency or coefficient of performance is given by the terms like Q or in terms of heat exchange, okay, if we replace these terms by their corresponding temperature of those thermal reservoirs, then this gives us the thermal efficiency or thermal coefficient of performance. Now we require to find the maximum coefficient of performance, so replacing the heat exchange, okay, heat exchange at lower thermal reservoir with the corresponding temperature of that thermal reservoir will give us the coefficient of performance for Carnot, reverse Carnot engine. Okay, reverse Carnot cycle. That cycle would be giving us the maximum COP. Okay, so they have clearly mentioned that whatever your actual COP is. Now let us find out what is going to be our actual COP. Okay, this is for Carnot cycle. This you can say this is going to be sorry, not this. This is going to be your maximum Carnot cycle. Okay, or sorry, maximum coefficient of performance. Okay, so they have given that actual COP is going to be 0.75 of or 75% of maximum COP. Okay, this is going to be 75% of the maximum COP. Now, what is going to be the actual COP? Actual COP, we have found out earlier that actual COP is nothing but refrigeration capacity divided by power input, or you can say refrigeration effect by W net, okay, or W input. Okay, So if we multiply mass flow rate with both the terms in numerator and denominator, then this will be the case. RC or refrigeration capacity divided by power input, okay, equal to what? 0.75 into this one. Now these temperatures, okay, TL divided by TH minus TL are in absolute temperatures, okay, but these are given in degree centigrade. Absolute temperature means we need to find them in terms of Kelvin, okay, the unit must be Kelvin, okay. So find the temperatures in Kelvin. If you want to find out the lower temperature, this is given as minus 30 degree centigrade, okay. So if you add 273 with it, it is going to give you the temperature or actual absolute temperature, that will be in Kelvin. So if you do minus 30 plus 273, it is going to be 243 Kelvin, okay. So this will be the lower temperature in absolute scale, okay. Now if you want to find the higher temperature, same procedure, you need to add 32 degrees given, okay, you need to add 273, okay. So the amount you are going to find out is nothing but 305 Kelvin, okay. 305 Kelvin is going to be your a higher temperature, okay. Now put these values in the equation, okay. So in place of this COP max will come here. So in the numerator it is TL. TL is what? 243. 243 is given. Now TH minus TL. TH is what? TH given is 305 Kelvin, okay. 305 minus of 243. So if you do this, then the result, and this RC, okay, this refrigeration capacity is given in terms of 5 kilowatt, okay. So in place of refrigeration capacity I am writing 5, okay. 5 means this is given as RC equal to 5 kilowatt, okay. So what is going to be the power input? The power input is going to be 1.7 kilowatt, okay. The power input you can find out from here, this would be 1.7 kilowatt, okay. So these calculations has been previously done, okay. So if I calculate here, it would be taking a longer time, so I have directly written down the result here. If you simplify this equation, you are going to get that power input from this question is going to be 1.7 kilowatt. Likewise, reverse Carnot cycle, we have reverse Breton cycle also. So if you remember, in the Breton cycle, it was a power producing cycle, okay. Now if you reverse all the processes in that cycle, you are going to get a refrigerator, okay. So that refrigeration is going to be working on the basis of reverse Breton cycle, okay. So previously it used to start from here, okay, and the compressor used to be there, okay. So after that, there used to be a heat addition and condenser used to be there, okay. Condenser used to be here. Now we are reversing this process, okay. Now it is starting from the compressor. If you look at the PV diagram and TS diagram also, previously the Breton cycle used to start from this point, okay. So after this completing a cycle in clockwise direction, it used to come here. Now it has started from here, okay. From the compression it has started from 1 to 2 is going to be adiabatic compression, okay. Similarly in TS diagram or temperature entropy diagram, 1 to 2 is nothing but adiabatic or reversible adiabatic or isentropic compression, okay. Then after 2 to 3 is what? This is heat rejection, okay. It is coming down, okay. It is coming down. If the arrow was in this direction, okay, this direction, then it would have been heat addition because temperature would have increased. Now 2 to 3 temperature is decreasing. From this is temperature line, okay. From 2 to 3 temperature is decreasing, so this is going to be heat rejection. Similarly 2 to 3, okay, this is going to reject heat in constant pressure, okay, constant pressure condition. So this is constant pressure line in TS diagram, this is constant pressure line in PV diagram. So in constant pressure it is going to reject heat, okay. Then after 3 to 4 it is going to expand, okay. 3 to 4 it is going to expand, okay. After expansion, whatever the substance that is coming out will be in liquid form. Then in evaporator it is going to get evaporated again, resulting in taking away some heat from the storage where we need to keep a temperature, okay, less than the required temperature, okay. So from here the heat is going to get up. So this is from this region the heat is going to up into the system, okay, and it is going to get rejected via process 2 to 3. Similarly, in TS diagram, 4 to 1 is going to be heat addition to the system from the storage. It would be heat addition from the storage to the system. Okay, this is the system. So to the system heat is getting added, but from the storage, then here is a storage where we need to keep a temperature. This is going to be T low, where we need to keep a temperature lower than a certain temperature. From here heat is going rejected and adding up to the system. That's why 4 to 1 temperature is increasing. Okay, and it is also evaporating. Okay, so that is the reason the temperature is increasing from 4 to 1. So this is going to be our reversed Breton cycle. Okay, so now if you want to find out the COP would be again the same only. Okay, whatever the work input you are going to give, this is going to come in the denominator, and whatever the refrigeration effect that is the amount of Q2, that is the amount of heat that has been taken away from the space, is going to be the refrigeration effect. Okay, so this will be the COP. In Carnot cycle, you could have written the coefficient of performance in terms of temperature also, because if you write it in terms of temperature, then it is going to give you the maximum COP. But since it is Breton cycle, not a Carnot cycle, that means the temperature, the COP temperature term is not going to be there. Rather, you can write it in heat exchange form. Okay, rather you can write it in heat exchange form. That means you can write it in QL divided by QH minus QL. Okay, now if you want to know where it has come from, W work input is nothing but this equal to this has just come from the first law for a cycle. Okay, so first law for a cycle is what? First law, work interaction is equal to total heat interaction. Okay, so total heat interaction is going to be total heat interaction. Okay, so from this equation you are going to find work input is going to be QH minus QL. Okay, and refrigeration effect means what? Whatever the amount of heat it is been taking out from the lower temperature, that is nothing but QL, and it is also known as refrigeration effect. So this is going to be our COP for reverse Breton cycle. Okay, now we are going to start with vapor compression refrigeration system, or known as VCRS. Now we are going to study about the vapor compression refrigeration system. Okay, so in vapor compression refrigeration system, the procedure is going to be completely same. Okay, the procedure is going to be completely same, but there is only one difference would be there. This is going to be vapor compression. Okay, so that means inside the, unlike the other cycles, there it is going to be a phase changing process. Okay, or you can say whatever the working fluid that has been traveling throughout the machine parts. Okay, there are several machine parts like compressor, condenser, evaporator, and the expanding device. Okay, throughout this, whatever the working fluid has been moving, okay, so those these working fluids are changing phase now. Okay, and the other thing that has been different from the Breton cycle and Carnot cycle is that in both those cases, okay, Breton cycle and Carnot cycle, okay, the expanding device was a turbine. The expanding device, that means whatever the device was there which was expanding the substance that was coming out from the condenser, was a turbine. Now in vapor compression refrigeration system, this is going to be a throttling device. Okay, this is going to be a throttling device. So we are replacing the turbine with the help of a throttling device, and the different parts are going to be same now. Okay, now from 1 to 2. 1 to 2 means with the compression. So after whatever the substance that has been coming out from the evaporator is going to be gaseous. Gaseous means, evaporator means what? It is going to evaporate whatever the liquid term is going to enter into this evaporator. This evaporator is going to turn it into vapor. So after vapor has been formed, this vapor has been compressed through a compressor. Okay, after that it is passed through a condenser. Okay, condenser is what? Condenser is again a phase changing device, which is going to change the phase of a system from gaseous to liquid. Okay, so this is going to be, there is going to be a condenser. So whatever the gas, compressed gas that has been coming out is now passing through the condenser to form liquid. Okay, is now coming out through the turbine to form liquid. After that it is passed through a throttling device. In throttling device, what happens? It is going to expand. Expand means what? Is temperature is going to come down. Okay, passing through this throttling device, it is going to expand, and due to this expansion, its pressure is going to release now, and the temperature is also going to come down. So due to this fall in temperature, what happens, some of the and due to the expansion and due to the loss of pressure, okay, due to the loss of pressure, now we all know at lower pressure the boiling point comes down, okay, the boiling point comes down. So due to the loss of the pressure, some of the liquid, okay, there was complete liquid, so some of the liquid has been converted into gaseous form, okay. So liquid plus this liquid plus gaseous part is going to come out through the or it is going to pass through the evaporator. So after passing through the evaporator, the total gaseous part is coming out of the evaporator now, and the cycle then continues. Okay, now coming to the TS diagram. Now since here there is a phase changing process, so again the vapor dome will come into picture. Okay, the vapor dome will come into picture. So there is temperature entropy diagram. Okay, temperature entropy diagram. In temperature entropy diagram, 1 to 2 is what? 1 to 2 is nothing but adiabatic compression, or you can say isentropic compression. So 1 to 2 is going to be adiabatic compression. 2 to 3 is what? 2 to 3 is at constant pressure it is going to release heat. Okay, so you can say this is going to be a constant pressure heat rejection process. Okay, this is going to be a constant pressure heat rejection process. After that, 3 to 4. Now if you remember the open system processes, we have derived what is going to be the work done or heat transfer or something like that in for all the open system devices like compressor, turbine, throttling device also we have said. Now if you remember, in throttling device we have said that, or we have derived that H1 was equal to H2. That means whatever the process that is passing through the throttling device is going to be an isenthalpic process. Isenthalpic process means the enthalpy is always going to be same. Okay, the enthalpy before passing through the throttling device and after passing through the throttling device is going to have the same enthalpy value. So this isenthalpic process is now represented from process 3 to 4. Okay, to make you better understand, we are drawing one pH diagram also, that is pressure versus enthalpy diagram. In that the vapor dome goes like this. Okay, now 3 to 4 is isenthalpic process. Now this is the enthalpy scale. Okay, so 3 to 4 is going to represent the isenthalpic process, and it is going to have the value of enthalpy, whatever the enthalpy value is going to be there. Okay, so 3 to 4 is again going to be an isenthalpic process. Okay, now 4 to 1 is what? 4 to 1 is nothing but it is the heat input to a system. Okay, heat input to the system, but heat rejection from the space where we need to maintain the temperature. Okay, so this is 4 to 1 is going to be a heat input to the system, and 1 to 2 is again this is going to be a compressor work. Okay, similarly in pH diagram, or you can say pressure and enthalpy diagram, 4 to 1 is what? 4 to 1 is going to be at constant pressure it is going to add up heat into the system from the space. Okay, so 4 to 1 is going to be our constant pressure heat, and then 1 to 2 is going to represent your isentropic compression. Okay, or reversible adiabatic compression. So in pH diagram, this is how the isentropic process is represented in pH diagram. Okay, so this is the basic layout of a vapor compression refrigeration system. Now we'll see the analysis. Okay, after that we are going to start vapor absorption refrigeration system.